Right. Let us now discuss Bragg's law or Bragg's equation. Okay. According to Bragg, they made some assumptions. Let us list down. According to Bragg's, each lattice plane, each lattice plane in a crystal behaves like a line in a diffraction grating. Okay, in the previous video I explained the optical grating, which are made up of large number of lines very closely spaced to each other, and each line diffracts visible light. So similar to that, Bragg proposed that each lattice plane in a crystal behaves equivalent to a line in a diffraction grating, but the only thing is these lines diffracts X-rays. So this is acting as a diffraction grating to X-rays, not visible light. So I have drawn a lattice, a two-dimensional lattice here. What do you mean by two-dimensional lattice? It is systematic, periodic, and regular arrangement of lattice points in two dimension. Each line that I have drawn in two dimension, it is a lattice line, but in three dimension each line is actually a plane. So ನಾನು ಇಲ್ಲಿ ಡ್ರಾ ಮಾಡಿರೋದು ಟಾಪ್ ವ್ಯೂ. ಸೊ ಪ್ರತಿಯೊಂದು ಲೈನ್ ಏನಿದೆ ಎ ಎ ಬಿ ಬಿ ಸಿ ಸಿ, actually it is a plane. Each plane is perpendicular to the plane of the screen. Okay, and each plane contains several lattice points, which are nothing but atoms, molecules, or ions of the crystal. So according to Bragg, each of this plane acts in a similar way to a line in optical grating. The only difference is the lines in optical grating diffract visible light, whereas the lattice planes in the crystal diffract X-rays. And in fact, they assumed that these planes behave like a reflection grating. This is a very strange assumption which is far from reality, but still it is accepted, as I already told you, because the final answer that we obtained by using Bragg's equation is same as the experimental result. Okay, so this is very vague. They assume that each of the lattice plane acts as a reflection grating. So what are they assuming? They are assuming that diffraction from crystals are nothing but a series of reflection from each of the lattice plane. Remember, in reality it is diffraction of X-rays, but according to Bragg's law it is reflection of X-rays from each lattice plane. So each of the lattice planes act as a mirror. ನೀವು ಆಪ್ಟಿಕ್ಸ್ ಅಲ್ಲಿ ಮಿರರ್ ಬಗ್ಗೆ ಓದಿದಿರಿ, ಮಿರರ್ ರಿಫ್ಲೆಕ್ಟ್ಸ್ ಲೈಟ್. ಸೊ ಅದೇ ರೀತಿ each reflection grating or each lattice plane acts as a semi-transparent mirror to X-rays. What is the meaning of semi-transparent mirror? Okay, when a light falls on a mirror, if part of light is reflected and part of light is transmitted through the mirror, then this mirror is called as a semi-transparent mirror, because part of light is reflected and part of light is transmitted. So according to Bragg's, okay, each of this lattice plane acts as a semi-transparent mirror to X-rays. What does it mean? When X-rays pass through each of the lattice plane, part of the X-ray is reflected, part of the X-ray intensity is transmitted. Okay, so let us consider reflection from two planes, say for example plane AA and plane BB. Okay, so I have a source of light somewhere here, a source of light. So X-rays fall on the crystal. Say for example X-rays falls on the lattice plane AA, and part of the light X-ray is reflected. Remember, it is actually diffraction taking place, but according to Bragg's picture or approach, it is a reflection of X-rays. Okay, so let me take this point as L, where the X-rays originate, and this point where X-rays falls on the lattice plane, I will take it as M, and I will take this as N, okay, which is nothing but a point very close to the detector which detects X-rays. Okay, now let us consider this angle, glancing angle theta, which is nothing but the angle of incidence. According to laws of reflection, angle of incidence should be equal to angle of reflection. So this angle of reflection should also be same, that is theta. Now, as I already told you, this mirror acts as a semi-transparent mirror. It means part of the X-ray is reflected, whereas the remaining part is transmitted, and that transmitted X-rays will fall on the next plane, through which one part of the X-rays will be reflected and the remaining part of the X-rays will be transmitted, which will be successfully reflected and transmitted from the next planes. Okay, now let us consider another X-ray beam falling on the next plane. Okay, so I have another X-ray beam falling on the next plane, part of which is reflected and remaining is transmitted, and successive planes will do the same thing. Part of the intensity is reflected, part of the intensity is transmitted. Now let me take P as the point from which the X-rays originate from the source. Okay, the point of contact between the X-ray and lattice plane, I will take it as Q, and the point where these X-rays are detected by the detector, I will take it as R. So there are two X-ray beams reflected from two neighboring planes reaching the detector. Now, as I already told you, since these are lights, they interfere with each other. Okay, strictly speaking, they are nothing but light waves. They are light waves. Okay, they are light waves. Of course, I am not drawing neat diagram. Okay, they are light waves reflected. Okay, and they are reaching the detector. Now these light waves superimpose with each other. Okay, these X-rays interfere or superpose with each other. Now that results in either constructive interference or destructive interference. Okay, before that let me uh, remove this wave nature. Yes, okay, I have removed the wave nature so that we can clearly see this diagram. Okay, so the let me write the intensity of the X-rays reflected from the crystal, that is different planes of the crystal, and reaching the detector depends on the whether these beams, reflected beams, undergo constructive or destructive interference. Okay, what is constructive interference? If you have two waves which are exactly in phase with each other. What do you mean by in phase with each other? Crest of one wave falls on the crest of other wave, or trough of one wave falls on the trough of the other wave. So they are in phase with each other. If two waves are in phase with each other, they undergo constructive interference. Okay, and you get a resultant wave which is having greater amplitude. So as the amplitude increases, intensity also increases. So you should observe a bright spot in the diffraction pattern. Suppose if the two reflected X-rays are out of phase. What do you mean by out of phase? Okay, out of phase means the crest of one wave falls on the trough of other wave. The trough of other wave falls on the crest of other waves. So positive phase of the amplitude when added to the negative phase of the amplitude, they get exactly cancelled and you get nothing. Okay, wave gets cancelled and you get a dark spot or no spot in the diffraction pattern. Okay, so if you want to observe a spot in diffraction pattern, then the reflected X-rays should undergo constructive interference. If the diffracted or reflected X-rays are out of phase, we will see nothing in the diffraction pattern. And when I say diffraction pattern, what we have to observe in the diffraction pattern is the one spots that are visible. Okay, dark spots are not visible, so we cannot concentrate on dark spot. We have to concentrate on the bright spot, where this bright spot occur, what is the intensity of the bright spot. All those informations are very important. So what is the condition for obtaining a bright spot? The reflected X-rays should be in phase with each other, because of which they undergo constructive interference. So what is the condition under which the two reflected X-rays will be in phase with each other? A mathematical condition ನಾವೀಗ derive ಮಾಡಬೇಕು. So let the distance between these two planes be d, or you can also write it as GHKL. Okay, now I am trying to connect Miller indices and X-ray diffraction. Okay, HKL represents the Miller indices of all these planes. So all these planes are having same Miller indices HKL. So DHKL is the distance between two adjacent mirror planes, which I have shown by a blue line. Now if let me draw some lines, okay, geometrical lines. What I will do is, from here, from point M, I will drop a perpendicular on this line PQ. So this is perpendicular. Adhe riti from M, I will draw another line, okay, which is perpendicular to QR. Okay, perpendicular to QR. Let this point be X and let this point be Z. Now we observe carefully. Okay, the point of origin of both X-ray beam is from the same source. Also the point the two reflected X-ray beams reach, their destination is also same, the detector. Okay, if you see the diagram, the two diffracted X-rays travel the same distance, okay, up to here, and also the diffracted X-rays travel the same distance here also. But in this region, okay, here what we observe is the second beam PQ is traveling an extra distance XQ here before reflection. Adhe riti, after reflection, the reflected beam QR is traveling an extra distance QZ. Okay, let me simplify the figure. It looks clumsy. So what we are observing here is the beam, second beam PQR is traveling an extra distance compared to LMN. How much extra distance? An extra distance of XQ plus QZ. Okay, so let me write this. The second beam PQR travels an additional or extra distance of XQ plus QZ than the first beam